Hello everyone, welcome to session 3. In this session we will solve our questions on hydrostatic forces on surfaces. Okay, so as I have talked earlier, so hydrostatic forces, let me start with some basic introduction or basically formula. Okay, hydrostatic forces on uh, inclined surface, let's say inclined surface. Okay, and this formula for this is F is equal to WA x bar. Okay, and your height of center pressure or depth of center pressure is given by h bar. Okay, or since I have used here x bar, let's use h bar here. Okay, h bar, okay, is equal to h bar plus ig times of h bar times of sine square theta. Okay, so this is your force value and center pressure, or I can let me rearrange this to okay, fine. Okay, and next, if we talk about your curved surfaces, only these two are the main topics here. Okay, in hydrostatic forces. So hydrostatic force on curved surfaces, curved. So in case of curved surfaces, we generally do it in the two component system. Okay, we calculate your horizontal and vertical components. So horizontal component, or if I say FH, that is equal to WA h bar. Okay, same as we have done till now, and this AH is basically your horizontal projection in vertical plane. Okay, AH h bar, this is your horizontal force. If I talk about vertical force, this vertical force FV is equal to rho GV. Okay, where your volume V is volume of water up to your free surface. Okay, V is the volume up to free surface. AH is your projected area on vertical plane. Okay, now these are few examples for your for different surfaces. I have mentioned area, center of gravity, their moment of inertia about CG, and center of pressure. This I have also mentioned in your class lecture also. Okay, so now we will start with our questions. So this is our first question. A room in a lower deck of cruise ship has a 30 centimeter diameter circular window. If the midpoint of the window is 4 meter below the surface, okay, so this is your resurface here. Determine the hydrostatic force acting on the window and the pressure center. Take the specific gravity of sea water to be this. Okay, so we have to find the value of hydrostatic force acting. So hydrostatic force, I can write hydrostatic force F. So let me write it on the pen. So F, I can write it as your rho G A times of h bar. Okay, if I substitute the value, so rho is equal to 1025, G is your 9.81 into A area for this circle will be your pi by 4 times of d square. Pi by 4 into d square is 30 centimeters, 0.3 square, 0.3 square, okay, into h bar. H bar is given as your this 4 meter, okay. So let me multiply these terms here. So 1025 into 9.81 into pi, that is 3.142 divided by 4 into your 0.09, okay, into 4. So this turns out to be your value of F, or hydrostatic force, is equal to 2.84 kilonewton, okay. This is for answer for first part. Second, it is mentioned and the center of pressure. So we can calculate center of pressure, that is HP is equal to H bar plus Ig upon AH bar of sin square theta. Here this term will become 1, because you like it is in this window will be in your vertical plane, okay. So your theta will be 90 degree. If you substitute the values here, so your H bar we know that is equal to 4 Ig. So moment of inertia, as I mentioned earlier, for circle, your this is your circle, okay. For this moment of inertia is pi d square, pi d power 4 by 64. So pi into d to the power 4. So d becomes 0.3 की power 4 divided by 64, okay, into a, that is pi by 4 into d square, that is 0.3 square, okay, a into h is your 4. It's become like this, okay. Okay, now if you solve this, so 4 and 4 will cancel out, pi and cancel out, so this will only left with square here, okay. So 4 plus 0.09 0.3 square divided by 64 so this becomes HP is equal to 4.01 001 meter, okay. So you can see although like the difference between H bar and HP is very small, that is of 0.001 meter, that is 1 mm, but it still exists, okay. And that is when your this diameter of the pan is 30 centimeter and the height is 4 meter, okay. Now the smaller the area of this glass window will be, the lesser will be the difference between H bar and HP, okay. So now we will so with that this question is done. Determine hydrostatic force acting on the window and the center pressure, okay. Now we will move to next question. So 6 meter high, 5 meter wide rectangular plate blocks the end of the 5 meter deep freshwater channel. The plate is hinged about a horizontal axis along its upper edge here through a point A and is restrained by opening a fixed ridge at point B. Determine the force exerted on the plate by the ridge. Okay, so this ridge will apply certain okay, so let me put it like this. So due to the pressure distribution here, so here there will be distribution of pressure here will be 0, here pressure will be rho gh, okay. Now due to this your there will be your like net effective force F, okay, will be or your hydrostatic force F will be acting on the plate, and this ridge will be producing an force, let's say RB reaction on the road, such that your this road remains stationary at this point only, okay. So now to calculate this, what we can do, we can first we have to calculate the value of F. So hydrostatic force F is equal to given by rho g a h bar, okay. Now this rho g is your rho is since it is water, so we will take it as 1000. G is your 9.81 into your area if we talk about, so this like the area of the hydrostatic action is 5 meter by 5 meter wide. So area is 5 meter into 5 meter, okay, into h bar. H bar is here will be, so your h bar will be from here, okay, from the free surface only, and this value of h bar will be your 2.5 meter. 2.5 meter, half of the this distance, okay, because it is a rectangular shape, okay. So into 2.5. Now if we solve this, so 9810 into your 25 into 25, sorry, 2.5. So this will come out to be F is equal to 613.125 kilonewton. 125 kilo Newton, okay. So this is your hydrostatic force that will be acting on the plate, okay. Now if I want to calculate the reaction force or force exerted by, on the plate by a ridge, so what I can do, I can equate, like for equilibrium of the plate, for equilibrium I can say that summation of moment about A would be equal to 0, or should be equal to 0, okay. And moment about A will be your, like F into here this distance here, okay, this distance let's say is your x, okay, into x is equal to your RB times of total distance is 6 meter, this, okay. So your RB value will be, RB is equal to, F is given as 613.125 kilonewton. So let's convert it into Newton, or let's keep it in kilonewton only. So our answer will be kilonewton divided by 6 times of x. Now we don't know the value of x. To calculate x, so we can write x is equal to your 1 meter, this 1 meter plus height of center of pressure plus HP. Now I can write it as 1 plus h bar. H bar is your 2.5, or let me write the formula first. That is your h bar plus Ig upon Ah bar, okay, for vertical plates, is equal to 1 plus 2.5 is h bar plus Ig for rectangular plate is bh cube by 12, okay. So B here your B is width, that is 5 meter, 5, and h is the height, that is 5 meter, bh cube by 12 into A, area is 5 into 5 into h bar is again 2.5, okay. So here your 5 into 5, and like if we can write 2.5 as 5 by 2, okay, into 5 into 2, okay. So 5 cube, okay, and 2 6. So if we calculate this, so this will become 3.5 plus 5 divided by 6. So this comes out to be 4.33. So your x is equal to 4.33 meter, okay. And if we see here, like since this dimension is considerable, so we can say that see that from here, like your difference between the height of your CG and CP is your 5 by 6, and this 5 by 6 is your 0.83. So around 0.83 centimeter is the gap between your h bar and HP, okay. So if you substitute the value of x here, so you will obtain RB is equal to your 613.125 into x, that is 4.33, divided by 6. This comes out to be 442. So 442.47 kilonewton, okay. So this is your force exerted by the ridge on the plate, okay. Now we will be moving to our next question, that is this one. For a gate width 2 meter into the paper, okay, 2 meter into the paper, determine the force required to hold the gate ABC at its location. So this is your gate ABC. Now if you see here, so there are two fluids on the same plate here, okay. So we will consider let's say F1 to be force acting here, F1 to be force acting on this surface, F2 to be the force acting on this surface, F2, okay, and F3 to be the force acting on this surface, okay, because they are like we can break the surface into three parts now, okay. I hope you get this point, okay. Now what we will do, we will calculate each and every force and their center of pressures, okay. So your F1 value, F1 equal to rho 1, that is your 860 rho 1 G1, so or G is will be constant 9.81 into H is your rho G, A is your like 10 centimeter and 2 meter into D, so 2 meter into 0.1 meter is your height here, so this is your area into X bar or H bar is your 5 centimeter here. If you look into this part only, so this will be 5 centimeter. 5 centimeter is 0.05, okay. So if I multiply this, so this will be 860 into 9.81 into 0.2 into 0.05, okay. So this comes out to be your F1 is equal to 84.37 Newton, okay. Next we will calculate your H1 value, okay. So H1 will be H1, okay. So let me write the formulas here so that I won't be writing it again and again here, okay. Or I can directly write it here only, because of some space constraint. If we proceed like this, we will be left with less space. So here we have obtained 84.37 Newton, okay. This is the value of F1. If I calculate HP1, so HP1, let me write the formulas here first. So your H is written. So and one more thing, like here I have mentioned F2 and F3 now. So this ABC can be as also assumed as a curved surface, okay. Like here we can distribute into horizontal components and vertical components, okay. So FH or F, if you talk about your in simple flat plates, so this will be equal to your rho G A H bar, okay, and your FB is equal to rho G V, okay, rho G V. So I will use these formulas only, okay. And now HP, okay, one more thing, like HP is given by H bar plus Ig upon H bar sine square theta, okay. So I will write it here. So H bar here will be your 0.05 meter, 0.05 plus Ig is BH cube by 12, so B here is 2 meter, 2 into H is your 0.1 cube by 12 into your area is your 2 into 0.1, okay, into H bar is again 0.05, okay, into sine square theta will be your 90 will be 1. This will become 1 because it is a vertical surface. Now if we solve this, so this will become 0.002 divided by 12 divided by 0.2 divided by 0.05. So this comes out to be is equal, okay, and add 0.05 in this, so this comes out to be 0.067 meters. This is your HP1. So your F2 will be given by F2 is equal to, so your SG is 1.23 here, so 1230 into G is 9.81 into area of plate is 80 centimeter by 2 centimeter. So 2 into 0.8 is area. Your h bar here will be your 40 centimeter. Okay, so into 0.4 meter. Okay, now if we solve this, so let me calculate the value first. So this is your 1230 into 9.81 into 1.6 into zero point 0.4. This comes out to be 7722.43 Newton. Okay, now we can calculate HP2. So HP2 will be given by h bar, that is your 40 centimeters, 0.4 meter, plus IG, that is BH cube by 12. So 2 into 0.8 cube divided by 12 into A is your 2 into 0.8 into your h bar. H bar is your 0.4. Okay, so if I solve this, so let's cancel out 2 and 2 here. Okay, that not show it here. So this will become 0.64 is your 0.8 square. Okay, divided by 12 divided by 0.4, so plus 0.4. So this comes out to be your 0.533 meter. Okay, now if I calculate your F3, so F3 is basically your vertical component of force. Okay, and its value is your weight of the liquid above this plate. Okay, so weight of the liquid till this point, and like this total fluid's weight, this total fluid weight will be your a value of F3. Okay, so let me write the weight, that is your rho gv. Okay, so for first one, your rho is 860 into g is common. Okay, into 9.81 into volume v volume is your 2 meter is depth. Okay, the total height here if I talk about, and volume for this will be your like this dimension into this dimension into depth. Okay, so your this dimension is 50, that is zero point 0.5 into this dimension is 40 meter centimeter, that is 0.4 meter into 2 meter depth. Okay, plus your this weight of this fluid, that is rho is your 1230 into g, that is 9.81 into volume is your 80 centimeter, 0.8 into 0.4 into 2 meter is the depth. Okay, so this would be equal to, so let me calculate it here, 860 into 0.5 into 0.4 into 2 plus 1230 into 0.8 into 0.4 into 2. Okay, now this multiply by 9.81, this comes out to be 11,000 11,097.07 Newton, 07 Newton. Okay, this is your F3 value. And if I talk about your so your center pressure will be at this level only. Okay, now for F1, if I let's say that we have, since we have to calculate this force F, so what we can do for equilibrium, this for equilibrium, summation of moment for this plate about hinge A should be equal to 0. Okay, so we have to calculate the distance of these forces from point A. Okay, so if I talk about this is, let's say x1 is distance from x1 is the distance from point A for F1. Okay, x2 is the distance for F2. Okay, and x3 is, this distance will be your x3. Okay, so your x1 value will be, from here we can write Let me write first here. That is your F1 times of x1 plus f2 times of x2. These both forces movements will produce your uh, clockwise movement for this like ABC section, plus also like F3 force will also provide, sorry, counterclockwise movement. Okay, all three forces will produce counterclockwise movement about A, and this force F will produce clockwise movement, that is F into zero point 0.4 will produce your clockwise movement, so this should be equal to 0. Okay, so I can find F into zero point 0.4 is equal to F1 is your 84.37 into x1. X1 we can say that x1 will be equal to your h1 hp1 only. Okay, 0.067. Okay, plus f2 value is we found out to be 7722.43 into x2. So if I talk about x2, so x2 will be this distance from here up to here. Okay, plus your hp2. I hope you get this point. Okay, so hp2 plus zero point 0.1, that is that will be equal to 0.633. Okay, so x2 will be equal to your hp2 plus zero point 0.1. Okay, and plus f3 is your 11,097.07 into x3 will be, this distance will be, so like this x3 will be act on the like center of CG, so this will be point half of 40 centimeters, so that's 20 centimeters, 0.2 meters. Okay, so from here we can find my value of f is equal to, so let me solve this first. So this will be 11097.07 into uh, 0.2. Okay, now plus 84.37 into 0.067 plus 7722.43 into 0.633. Okay, now divided by your 0.4. So we have obtained value of f is equal to 17,000. So f is equal to 17,000, so we can write 17.78 kilonewton. So this amount of force will be required to hold the plate at its location. Force required to hold the gate ABC at its location. Okay, so I hope you get this. Now let's move to your next question. So in this question, a semicircular gate of radius 1 meter is placed at the bottom of the water reservoir as shown in the figure below. The hydrostatic force per unit width of the cylindrical gate in y direction. Okay, so we have to basically find the vertical load on the cylindrical gate. So in this figure we can see basically that the pressure will be acting like this, downward direction up to like this point, and after this point the pressure will be in upward direction. Okay, so on any hydrostatic surface, as I mentioned earlier, is equal to your weight of the fluid above the surface. Okay, so we can say that if, let's say, if this is your hydrostatic surface like this, okay, up to semicircle, let's say take this point a between here to here. Okay, if it is like this, then let's say this is water here, so your vertical force will be total weight of the water up to this point. Okay, is weight. Okay, now if I talk about the second case, in second scenario, basically in second scenario what is happening, that we have considered this section here. Okay, so let's talk about this section. Okay, so in this section, let's say it's something like this. Okay, so this is gate. Okay, and this is your base. Okay, and your water is water is filled on, let's say, this side here. Okay. Okay. So in such cases, you're like still we will take the force will be acting in this direction. So the force on this will be equivalent to your like weight. Imagine a weight of the column, a column of water above this surface. Okay. So weight of this column will be acting on this surface. Okay. So if we consider this, so we have to like consider this is the downward force acting on this surface. Okay. And if we consider this surface, then the upward force acting on this surface will be total this weight. Okay, up to this point, not this point, sorry, up to like from here till here, up to this level. Okay. So if I talk about net upward force, okay, so let's say this is weight 1, this is weight 2. Okay. So upward force, if I talk about Fv, so I can write it as weight 2 that is greater than your weight 1. Okay. Now what we will be left with? Okay, so this is your Fv, this is your Fv1, this is Fv2. Okay, so Fv is this. So this Fv will be your weight of water, weight of water contained within the volume, Okay. So we are only left with the, like, if I remove all these drawings from here, so I am only left with this volume. Okay. So the volume or the weight of water inside this volume will be your net vertical force. Okay. So I can say that my Fy will be equal to your rho g into V. Now V we have to take of this. Okay. Now it is mentioned that gate has radius of 1 meter. Okay. So pi into r square is, this is area, into 1 unit depth. You mentioned per unit depth width. So this is your volume. So from here I can write it as your pi rho g is your uh, Fy. Okay. Now if you substitute the value of pi yg, so rho, since it is mentioned as water, so rho is 1000, so 9810, let me write it as pi into 9810. Okay. So this comes out to be your 30.8 kilonewton. Okay. I hope you get the solution. Okay. Like whenever there is a surface like which is curved on both upside and downside. Okay. If on the both side of surface, if the water is available, if the same liquid is available, then a net force because of that liquid on the surface will be your net amount of liquid that can be contained within that volume. Okay. Now we will be moving to our next question. So in this question, a tank in the figure is 3 meter wide. Into the paper, negating atmospheric pressure, compute the hydrostatic force, horizontal force, vertical force, and resultant force on the quarter circle panel BC. Okay, so we can write your horizontal force. A is your horizontal force, that is equal to your rho g horizontal force, area horizontal into h bar. Okay. Now horizontal area, how we will draw? We will like so very simple principle is that what we consider that there is a, let's say, a plane here, or basically a screen here, and we like to send light from this side. Okay. So this will like how it will indicate it from this point up to this point. Okay. So this will be your shape of your AH. Okay. And since it is mentioned 3 meter into the water, so it will be like rectangular. Okay. I hope you get this point. Okay. And the dimension of the rectangle will be 4 meter. This dimension is 4 meter and 3 meter is width, so this dimension is 3 meter. dimension is 3 meter. Okay, so 4 meter by 3 meter is the dimension of the projected area. Okay, so I can write the value of rho is equal to rho g as 9.9810 into ah. I can write it as 4 into 3. 4 into 3. Okay, now h bar, if I talk about, so h bar will be taken from the here. Okay, now this dimension is 6, so 6 plus 2 is your h bar. Okay, from the free surface only. So 6 plus 2, that is 8, is your h bar. So if I solve this, so I have obtained my fh is equal to, let me substitute the values, or sorry, calculate the values. So 9.9810 into your 12 into 8. So this comes out to be 941.76 kilonewton. So this is your horizontal force. Now if I talk about my vertical force, part B, that is Fv. So Fv is the weight of the fluid above this. Okay, so this total weight will be given by rho gv. So rho g is your 9.9810. Okay, into volume. So volume for this complete section, so volume for rectangular section will be your 4 meter, this dimension is 6. So 4 into 6 into width in the paper is 3 meter. Okay, plus now this area is your like radius. You can like, this is like a circle of radius 4 meter. So pi r square divided by 4 is your like area of this quarter circle, into depth is your 3 meters. Okay, so this is your rho gv. Now if I solve this, so your this will become 4 into pi into 3. Okay, and plus your 6 into 8, 4 into 18, 4 into 18. Okay, into 9810. So this comes out to be 1076.2 kilonewton. This is your Fv, vertical force. Now in third part, C part, it is mentioned to calculate resultant force on the quarter circle panel BC. So resultant force Fr is given as your square root of Fh square plus Fv square. Okay, so let's calculate these values. So square of Fv plus Fh is 941.76 square. Okay, so this comes out to be, okay, and then square root, this comes out to be your resultant force or total hydrostatic force is equal to 1430.07 kilonewton. Okay, so this is your resultant force. Okay, so these are the asked questions. There are 3 parts also. We have solved these 3 parts. Okay, now again, if you have to, let's say, calculate the location where will this force will be acting. Okay, resultant force and horizontal vertical force, where will they be acting? So let me make it clear here. So your horizontal force will be acting at the CP of this figure only. Okay, so let's say if CP lies here, so your horizontal force will be like this. Okay, FH. Okay, and vertical force will be on the CG of this figure. Now CG for this circular section will be like lying somewhere here, that is at 4r by 3 pi here, and for rectangular section is at 2 meter here. So for both of these, it should lie somewhere between here. So let's say that up to some point here only, there is your Fv. Okay, or okay, so Fv will be acting some line here, let's say end line, or here. Okay, okay, so something like this. You can calculate the value of Fv here. Okay, and then the resultant force will be acting on like both the intersection of your FV and FH. Okay, this is not entirely correct, like it cannot be scaled here, so these this thing is not exactly correct here. Okay, so it generally comes out like this, like your FH will act at, let's say, this point FH. Okay, so your FB will act somewhere here. Okay, and you can say that your F resultant, this is your F resultant. Okay, now we will move to our next question, that is this one. uh, a water uh, trough of a semicircular section of radius 0.6 meter consists of two symmetrical parts hinged to each other at the bottom. Okay, the two parts are held together by cable. Okay, this is cable, and turnbuckle placed every 3 meter along the length of the trough. Okay, calculate tension in each cable every 3 meters, so we will like consider your width to be 3 meter. Okay, calculate tension in the each cable when the tuff is filled to the trim. So it's something like this. So if I talk about a semicircular hinge, so it's like this. Okay, and it has a width of like on 3 meter, another one is at 3 meter. Okay, so it's like this. Let me draw it here so that we can see it clearly. Okay, it's something like this, and one side of it is filled with water. Okay, let's say it's something like this, it's filled with water on this side. Okay, so this is your water. Okay, now what will happen? Okay, but before that, what else is mentioned? That two cables, two. It is mentioned that there are symmetrical hinge at bottom. The part are held by together by cable and turnbuckle plate. Okay, so this cable will have tension T, and tension T here, and have length of L is equal to 3 meter. Okay, what else? If we see here, so there will be two forces acting. First one is your vertical force. First one is vertical force FV, and second one is your horizontal force FH. Okay, so if we get find, let's say, find your FV and FH and calculate their distance from the hinge. This is your hinge, so let's say this is your X, and this here is your, let's say, Y. Okay, and if I can find X and Y, so I can find your value of tension. Okay, so what I can say, that the horizontal projection of this surface will be in form of your rectangle. I hope you like understood this point here. Okay, so it should be something like this. It should be something like in shape of rectangle only. Okay, so this dimension will be 3 meter, and this dimension will be your equal to R, and this R is equal to 0.6 meter. It is mentioned radius is 0.6 meter. Okay, so what I can say here, so I can say that my FH value, and here basically this type of system can be concluded like this, like this part here is indicated by this diagram, and the reverse of this will be like similarly for this part also we can draw a diagram. Okay, so we are now considering only the right hand portion. Okay, so your FH value will be, FH is equal to rho g into A into H bar. Okay, now I can say that my rho, since it is mentioned in water, so this will be 9810 into A area is your 3 meters is like this length, and width is r, that is 0.6. Okay, into h bar. Now h bar is the half of height, that is 0.6, half of 0.6, that is 0.3 meter. I hope you get this point. Okay, now if we solve this, so this will be 9810 into 1.8 into 0.3. So this is equal to 5.3 or 529, sorry, 5297.4 Newton. This is your FH value. If I talk about FV, so FV is equal to weight of the liquid, okay, above this surface up to free surface, is equal to rho g is again 9810 into volume. If I want to write the volume, so volume will be first area. Area is equal to pi r square by 4 into length is L. This is area. Okay, so 9810 into pi into r square. R is your 0.6. 0.6 square by 4 into L is your 3 meter. Okay, so if we solve this, so this will be 9.81 into pi is 3.142, 142 into your 0.6 square, 0.36 into 3 divided by 4, 8 point, sorry, this FV is equal to 8322.2 Newton. Okay, this is your FV, this is your FH. Okay, and if I want to write dimension x and y, so x is your like CG for uh, this semicircular section. CG for semicircular section is your 4r by 3 pi. Okay, is equal to 4, and we know that r is equal to 0.6 is given. Okay, so 4 into 0.6 divided by 3 divided by pi, this is equal to 0.255 meter. Okay, and I can write y is equal to r minus hp. Okay, and r is your 0.6 minus hp is your h bar, that is your 0.3, plus ig for this would be equal to, here we will consider rg for this protected area only. Okay, so protected area ig is bh cube by 12, 3 into h cube is 0.6 cube divided by 12 into 3 into 0.6 into h bar is 0.3. Okay, so if we solve this, so we have obtained y is equal to, so let's solve this first. So this is 3 into 0.6, it is 0.36 divided by 12 divided by 0.3, this is a 0.1. So 0.1 plus 0.4, y is equal to 0.2 meter. Okay, x is equal to this and y is equal to this. So we have obtained value of your FH, FV, x and y. Now if I want to, let's say, apply your for equilibrium, if I say that moment about O should be equal to 0, so from here what we can write? We can write that 2t times radius r is equal to your fh times of y plus fv times of x. Okay, so here we can find t is equal to, or let's write it exactly now. So 2t into 0.6 is equal to fh is your 5297.4 into y is 0.2 plus fv is your 8322.2 into your x is your 0.255. Okay, so if we solve this, so this will be 5297.4 into 5297.4 into point 0.2 plus 8322.2 times of your 0.255. Okay, now divided by your 1.2. So it will, so you have obtained your tension T is equal to 2651.4 Newton. Okay. Okay, so I should mention here, so like this T should be like basically T by 2 here. Okay, T by 2, T by 2. Why this T by 2? Because like on the both side, like it is mentioned na, at every 3 meter along the length of the trunk. Okay, so every 3 meter there are two ties. Okay, there is a tie, there is a cable there is a cable. Okay, now like each cable will support both hand sides, so this will be T by 2 here, T by 2 here. Okay, so here it would become T only, T, and your force will become after it multiplied by 2 into 2, so this becomes 5302.74 Newton. Okay, or I can write 7 Newton. Okay, I hope you get this solution. Now we will be moving to your next solution, that is this one. A 4 meter long quarter circular gate of radius 3 meter and negligible weight is hinged about its upper edge A. Okay, the gate controls the flow of water through length over the ledge at B. Okay, when the gate is pressed by the spring, determine the minimum spring force required to keep the gate closed when the water level rises to A at upper edge of the gate. Okay, so when this is the water level, we have to determine minimum spring force that should be required at this point. What should be the minimum spring force? Let's say that Fs is the spring force required to keep the closed gate closed. Okay, and your forces acting would be acting here would be your Fh and Fv. Okay, and since it is mentioned that the quarter circular gate of radius 4 meter long quarter circular gate, so its projection will be rectangular. Okay, where this side will be your equal to radius 3 meter. Okay, and this dimension will be your 4 meter long. So we can write your Fh value, that is horizontal force. Fh is equal to rho g A h bar. Okay, is equal to 9810 into A is your 3 into 4 meters is A, into x bar is 1.5 meter. Okay, so Fh is equal to, so if we solve this, so 12 into 1.5 into your 9.81. Okay, so this comes out to be 176.58 kilonewton. Okay, and if I want to calculate Fv, so Fv is equal to rho gv and will be equal to, so Fv will be your weight over the surface. Okay, so this volume of this amount of liquid, imaginary liquid, will be your Fv. Okay, and this amount of liquid volume will be your 9810 into, like, total rectangular volume of the rectangle, sorry, I mean cuboid, this cuboid. So this will be your 3 into 3 into 4 minus area of circle section. Okay, so let's, so here 3 by 3 minus this area will be pi r square by 4. Pi r square is 3 square by 4. Okay, into length is 4 meter. So if we solve this, so we have calculated our Fp is equal to 75.58 0.78 kilonewton. Okay, so we have calculated our FH and FV. Okay, so we have calculated our FH and FV. So if we calculate your distance from A also, let's say this distance is your X and this distance is your, okay, or let me write it in a different color. Let's say this distance is your X and this distance is your Y. Okay, so I can write that x is equal to this distance will be your centroid of this figure, that is 4r by 3 pi, 4r by 3 pi, and we will get this equal to, if I substitute r is equal to your 3, so I will get is equal to 4 divided by pi. Okay, which is equal to your 1.27 meter. Okay, now we can calculate y is equal to your hp, that is your h bar, that is 1.5 plus bh cube by 12. So your b here is 4 into h cube by 12, okay, into a is 4 into 3 again, into h bar is 1.5. okay, so this is y is equal to 2 meters. Okay, we have obtained x, we have obtained y. So what I can say, for this system to be in equilibrium, your summation of moment about a is equal to, should be equal to 0. Okay, so this would be your like fv into x plus fh into y. So these both forces will cause your anti-clockwise moment. Now this would be equal to your fs into r, which will cause your your clockwise moment about a. Now from here we can calculate our fs is equal to, because we know that r is equal to 3 meters, so let's solve these values first. So your fv is equal to 75.78 into x is 1.27 plus your fh, that is 176.58 into your y, that is 2. Okay, then divided by your r, that is 3. So we have obtained our fs is equal to 149.8 kilonewton. Okay, so this is a spring force required to hold the system together. Now let's move to next question. So in this question, the weight of the gate separating the two fluids is such that the system is in the static equilibrium. Okay, a weight separating two fluids. Okay, so this bar does have some weight, but its weight is such that it is balanced by your both fluids. Okay, like this system will become in equilibrium at this point. Okay, if it is known that f1 by f2 is equal to this, determine h1 by h2. Okay, so we can say here that in this liquid, if I want to calculate f1, so this will be your theta. Okay, and this is equal to your alpha basically here. Okay, so what I can say that f1 is equal to rho g a h bar. Okay, and this will be equal to rho will be 1860 into g is your 9.81 into a is your distance from here to here, and let's say 1 unit inside. Okay, let's say distance from this point to this point on this side is, let's say, L1, and on this side is, let's say, L2. Okay, from here to here is L2. Okay, so what I can say that my if I take this triangle here, this triangle, so I can say my sine alpha is equal to capital H by L1. Okay, and similarly I can write sin alpha is equal to small h by L2. Okay, so I can write here a is equal to this L1 into 1, L1 into 1 times of h bar. Now this h bar will be half of this height, that is h by 2, capital H by 2, which will be equal to your 860. So this will become 430 into 430 into G capital H, and if I substitute L1 is equal to h by sin alpha, so this will be G h square by sin alpha. Okay, so I hope you understood this point. We have evaluated f1. Now if I want to calculate f2, so f2 again I will substitute the values. So 1250 into 9.81, or let me write it exactly as G as it is here also, G into now this area. So area will be L2 times of 1. Okay, L2 times of 1, and h bar will be small h by 2. Okay, so we have obtained from here. Now if we solve this, so 625 into G h square by sin alpha. Okay, we have today L2 is equal to h by sin alpha. So we have been given that f1 by f2 is equal to 1.7. This is our given. Okay, now we will substitute the value of f1 and f2. So this will become 430 divided by 625. Now here it will become h square by h square is equal to 1.7. Okay, now if I solve this, let me solve it first. So this is 430 divided by 625. Okay, now inverse it, and multiply it with 1 by 1.7, and then take a square root of this. So this will become your capital H by small h is equal to 1.572. Okay, so it is okay, so asked is small h by capital H is equal to, so we will directly inverse it, the power minus 1. So this becomes 0.636. Okay, I hope you understood this. Okay, now moving to next question. So curved surface of dam is shaped according to the relation y is equal to x square by 9 as shown in the figure. The height of the water retained in a dam is 10 meter. Consider the weight of the dam to be unity. The resultant hydrostatic force acting on the dam is. Okay, so we have to calculate your both horizontal and vertical forces here, because this is a curved surface example. So let's say that, let's consider this to be origin at this point, this axis to be y, this axis here to be your x. So we can say that this point represented here 0, 0, when x is equal to 0, y is equal to 0. Now at this point we know that our y is equal to 10, y is equal to 10. Okay, so let's say if I have to calculate the value of x, so what I will do here is square root of 90. Okay, you get this now? Like if you substitute y is equal to 10 here, so 10 is your square root of 90, and this is equal to 9.49, let's say 9.49. Okay, comma 10 is the coordinated at point A. Okay, now if I want to calculate your FH, so FH will be rho g h into h bar. So your projected Dimension will be something like this. Okay, and this height is your 10 meter and this is your 1 meter. Okay, so this will be your now 9810. Ah is given by your 5 meter, sorry, 10 into 1. H bar is 5 meter. Okay, so we have obtained FH is equal to your 490.5 kilonewton. This is your FH, horizontal component of the force. Okay, horizontal component of the force. Now if I want to find my FV, so FV will be rho g V. Now to calculate the volume, we have to first calculate the area. Okay, so let's say that we have considered a strip at this point. Okay, here our width will be x. Okay, and at a distance y from the base. Okay, and this strip does have thickness of dy, so we can say that our dA, or let me write it dV, small unit volume, elemental volume is equal to, and that is dA into 1. Okay, since your width is unit, and you mentioned that consider the width of time to as unity, so dA can be written as your x times of dy. Okay, now I can write dV is equal to, if I want to write the value of x, so x will be your 3 root y, 3 root y dy. Okay, now if I want to integrate it, so I should integrate it from y is equal to 0 to 10. Okay, so volume of the water inside this will be 3 times of, now integration of root y is y to the power 3 by 2 divided by 3 by 2, and limit from 0 to 10. Okay, so this should be equal to, so V is equal to 3 times of, now this will be is 2 by 3 into 10 to the power 3 by 2 minus 0. Okay, so from here I obtained V is equal to, so 10 to the power 3 by 2 if I want to calculate, so 10 to the power 1.5 will be your root 2000 around, so this is your 31.62. Okay, into 2 is equal to 63.24 or 25 units. Okay, or cubic units, or cubic unit. Okay, or it is mentioned meter now. Okay, so let's write it in meter only. This is your meter cube. Okay, now if I substitute this value here, so I will get into 9.81 is equal to 620.44 kilonewton. Okay, so this is your FV. Now what is asked is simple thing, that is your related hydrostatic force. So F is equal to square root of FH square plus FV square. Okay, so we can write F is equal to, so FV square is 2 plus 490.5 to the power 2. Okay, now total power 0.5. This is your 790.9 kilonewton again. Okay, this is your total or resultant hydrostatic force, FR, let's say. Okay, now we will be moving to our next question. So in this question, water tank in the figure is pressurized. Okay, and showing the mercury manometer reading. Determine the hydrostatic force per unit depth on the gate AB. Okay, so first, in such type of questions, like there is no free surface of the water above, like in the container. Okay, the water doesn't have any free surface. What does it mean? It means that this system is pressurized. Okay, or like certain pressure exists inside the system. Like even if there is interface, there is a possibility that there is a gas inside, gas above the interface, and the gas is at higher pressure than that of atmosphere. Okay, so since so first let's find the pressure. So pressure, now here this will be your atmospheric pressure, or I can call it a reference pressure, or let me name this point 1. Okay, so I can simply say P1 is equal to, or at this point, like our point 1 will exist here, let's say. So P1 is equal to simple rho hg g into point 0.8. Okay, is equal to, if I calculate this, so this will be your 13.6 is the specific weight of specific density of your mercury, into g, that is 9.81 into uh, zero point 0.8 is the height. This turns out to be 106.73 kilopascal. Okay, this is a P1. Okay, now if I have to find the force and at surface AB, find the force at surface AB. So what I can do? So for this we have two methods basically. First is your method of pressure prism. Second is we have to since we have get the pressure P1, so I will calculate the height of column of water that should be originally there, such that the above pressure will be at atmospheric and there will be free surface. Okay, like I say here, the height of the liquid column required, height of water column, water column, let's say this, your x will be equal to your P1 by rho g is equal to, now this will be divided by 9.81 will be equal to 10.88 meter. Okay, so what does term indicate? This indicate that if I, let's say, remove this cover here and remove all the system here and increase the height of the system above this point by your 10.88 meter, then after 10.88 meter we will get a free surface, and we can like directly apply your formula, that is F is equal to W, or rho g a h bar, and this will be equal to like 9810 into a is your 2 into 1. Okay, 2 is height and unit depth. Okay, and h bar is your x, this x plus 5 is this distance, plus this one is half, sorry, 1. Okay, so if we substitute the value, so I will get f is equal to uh, this is 2, and this will become x is equal to, given as 10.88, so this will be 16.88 into 9810 into 2. So the f is equal to 331.185 kilopascal. This is your hydrostatic force on the AB. Okay, now as I mentioned about your pressure prism method. Okay, so in case of pressure prism, what we'll do, I will like draw a pressure prism here first. So here let's say pressure is your PA. Okay, and here your pressure is PB. Okay, and variation should be linear because your pressure variation in the depth with depth is linear. So we can write our PA, this is your PB. So PA is equal to P1 plus rho g times of 5. Okay, this side here, this will be equal to your, like initially P1 is 106.73 plus rho g into 5, so 5 into 9.81 is equal to 155.78 kilopascal. This is your P1, sorry, PA, and PB equal to uh, your PA plus rho g into 2. Okay, so this is equal to your 175.4 kilopascal. Okay, so we have obtained our P and PB, and this is like trapezoidal shape also only. Okay, now if I want to calculate F, okay, so I it is said that it is the your volume of prism, volume of prism volume prism is equal to area into like depth. So area is half into sum of parallel sides, that is your PA plus PB into your height, that is your 2 meters, into depth is 1 meter inside. Okay, so if I solve this, so PA plus PB will become 175.4 plus 155.78, so this becomes 331.18 kilonewton. Okay, this is your F on AB only. Okay, so from here you can say this term and this term both like both are generally same. So by using any method we will get the same result. So in this type of question we generally use your pressure prism, because instead of calculating your height of the water column, it will lessen the calculations, it will lessen our calculations. Okay, now let's see one more question here. So in this question it is mentioned that pressurized water fills the tank. Compute the net hydrostatic force on the conical surface ABC. So this ABC is conical surface which will have a base of your uh, base at AC. Okay, so let's say this point is 1, let's say this point is 2. Okay, and we are given that our P2 is equal to 150 kilopascal. Okay, okay, so if I want to write P1, so I can write it as P2 minus rho gh. Okay, and this will be equal to 150 minus 9.81 into, so it is kilopascal, so I directly use the specific density here, that is of water is 1. Okay, into h is 7 meter. Okay, and this will be equal to your P1 is equal to, so if you multiply solve this, so 150 minus 9.81 into 7, so this should come out to be 81.33. Okay, so this is a P1. Okay, now as I mentioned earlier, to calculate your hydrostatic forces, so there are two methods. First is pressure prism, second is to calculate the column of liquid water or liquid up to the free surface. Okay, so like here, since it is a conical surface, so our pressure prism method will be slightly difficult. So what would I do? I would calculate the water column height. Water height uh, for pressure P1, and let's say this value is x. Okay, and this x is equal to your P1 by rho g. Okay, and since P1 is in kilopascal, so let's divide this value 81.33 by 9.81, that is the value of G. So we have obtained X is equal to 8.3 meter. Okay, so we can say that after a distance of 8.3 meter, at a distance X, if we move from the surface, so here we will obtain our free surface. Okay, and pressure here will be PATM. So now to calculate your hydrostatic forces, I can say that for a submerged body, like this body is submerged, cone is submerged. So what will happen in this case? Your net horizontal force will be zero, because horizontal pressure will act from all sides, and that will be of equal magnitude at same level. Okay, like from both sides, your FH value will be same. So your net horizontal force is equal to zero, and the vertical force above the cone, if I talk about the surface, will be your weight of water column above the surface. Okay, so let me write it. So vertical force on conical surface is equal to your weight of the liquid. Okay, now this weight will be like here it will form a cylinder on the top and cone on the base. Okay, so volume, if I talk about of a cylinder and cone, so that will be your weight is equal to your rho g v. So rho g times of v is pi by 4 d square, that is 2 square into height is your x. Okay, plus your volume of the cone is 1 by 3 into pi I square, I mean that is pi by 4 d square, that is do square into height of the cone, that is 4 meter. Okay, so if you solve this, so this will cancel out this one, this here, this will cancel out this. Now if I solve this, so let me like x into 2 into pi. Okay, or 2, sorry. Okay, so pi into x is the 8.3. Okay, plus here it will become 4 by 3 pi, 4 divided by 3 into pi. Okay, into 9.81 is equal to, so conical surface force vertical force on conical surface is here 296.89 kilonewton. Okay, I hope you get this, how to solve this question. Okay, now let's move to next question. So here open settling tank is shown in the figure, contains the liquid suspension. Okay, determine the resultant force acting on the gate and its line of action. If the liquid density is 850 kg per meter cube. Okay, but the gate here is of like surface is of parabolic shape. Okay, so here we cannot use your direct formulas, because we don't know the area and moment of inertia for this parabola. Okay, so let's name these points to be A, this point to be B, and this point here to be C. Okay, so from B to C is our parabolic gate. Okay, and A to B is your fixed. Now let's consider that at a height h from the surface, we are considering an element. Okay, okay, So let's say this is an element, okay, and since it is like at a height h from the top, we can also say that on the plane at a distance y from the base, we are considering an element of thickness dy. I hope you get this. Okay, now okay, and before that let me proceed with one thing like sine theta. So the sine theta here, sine theta is equal to your perpendicular, that is 5 meter divided by AB. Okay, and also we can write, sorry, AC. Okay, AC. So from here we can write my value of AC is equal to, AC is equal to 5 divided by sine 60. Okay, 5 divided by sine of 60, that is your 5.77 meter. 5.77 meter. Okay, now now I can write that my AB here is your AC minus BC. Okay, and BC value is given as 3 meter. Okay, so we can write that my Y can be written as AC minus H by sine theta. Okay, so from here I can write my H is equal to, H is equal to AC minus Y times of your sine theta. Okay, now if we use it here, so I can write that my pressure on the elemental area P is equal to rho gh, and can be written as rho g times of h. H is your AC minus Y. Is AC basically we can also say is equal to length of the gate. Okay, let's say this is equal to length of the gate, so I can write it here L minus Y. Okay, so L minus, not the gate of the entire AB portion, AC sub portion. Okay, L minus Y times of sine theta. Okay, if I talk about the elemental force, so the elemental force will be your P times of dA. Okay, where your P is rho g times of L minus Y times of sine theta. Okay, times of dA. And now dA is your width. Width is equal to, this is your 2x is your width here. Okay, x on both sides, so 2x times of dy. Okay, and we can directly put x is equal to root 2y here. Okay, so your df can be written as df is equal to root, sorry, rho g sine theta into L minus y times of your 2x. 2x is equal to root 2y, root 2y. Okay, times of dy. Okay, so because we can write here x is equal to y by 2, sorry, root y by root 2, so this will become root 2y. Okay, now if we want to integrate this, so we can integrate it like I can write your f is equal to integration of df, and this will be equal to your root 2 times of rho g sine theta, rho g sine theta. Now since these terms are constant, and now the variable here is L minus y times of root y dy. Okay, and if I talk about the limit of y, so y is from 0 to 3, 0 to 3, from 0 to 3. Okay, so I can write f is equal to root 2 rho g sine theta. Now if we integrate this, so this will be L root y, so L times of y की power 3/2 into 2/3, okay, minus y की power 3/2 will become y की power 5/2 into 2/5, okay, and limit is still from 0 to 3, okay. So let's substitute the values here. So this will become f is equal to now this y bar, sorry, y here, we have to put 3, okay. So 3 की power 3/2, that is 1.5 times of 2/3 into L. Now your L value is here 5.77, okay. Now minus y की power or 2/5 into y की power 5/2, and y here is 3 की power 2.5. This comes out to be 13.75. Now let's multiply it by your root 2 and your sine theta, sine 60, okay, into rho g. Into g is your 9.81 and rho is given as your 850 kg per meter cube, 850. So your f is equal to 140.45 kilo Newton, okay. So this is your hydrostatic force acting on the plate. Now if I let's say I want to calculate your center pressure location, okay, center pressure location. So for center pressure we have to like calculate your moment about point C, okay. So dm, we talk about a small moment of inertia, so that will be df times of y, okay, and this is equal to your df into y. So your df here is this is your df, okay. So root 2 rho g sine theta times of your L minus y into root y dy, okay. Now if you integrate this, so moment is equal to integration of df into y, okay, and this can be also written as your root 2, okay, and I forgot to mention here y, okay. So root 2 rho g sine theta times of L minus y times of y की power 3/2 dy, and integration of this part from y is equal to 0 to y is equal to 3, okay. And we can also write your moment. Let's say that h bar or hp is your center pressure location. hp is your center pressure location. Let's say this is your center pressure location, okay, and your this force, that is F, is acting on this location, okay. So in this plane, like this distance will become hp upon sine theta, okay. So let me write it here. So this will, like, moment we can also write it as F into hp upon sine theta is a moment. This will be equal to root 2 rho g sine theta. Now if we integrate this, so this will become L into 3/2 plus 1 is 5/2, so 2/5 times of y की power 5/2 minus, now this is again y की power 5/2, so this will become 7/2, so 2/7 to the power y की power 7/2, okay, and this is limit from 0 to 3. So if you solve this now, so this is F into, okay, so F value we know as your 140.45 kilonewton. So 140.45 45. Okay. It is in kilonewton, so let's write it in newton. Okay, 440 450, this is in newton, divided by sine 60. Sine of 60 degree is equal to root 2 into rho is your 850 as mentioned in the question, 850 times of g, that is 9.81 into sine 60. Okay, now if you substitute the values here, so your L value is your 5.77 into 2 by 5 into y is your, we have calculated to be, sorry, y is 3, we have to substitute 3 to the power 5 by 2 minus 2 by 7 times of 3 to the power 7 by 2. Okay, and minus 0, so this whole term will become 0. So let's solve this here first. So this is your 5.77 into 2 divided by 5 into 3 to the power 2.5. Okay, minus 2 divided by 7 into 3 to the power 3.5. Okay, into root 2 into 850 into 9.81 into sine 60 okay, into sine of 60 again, divided by 140450. So this comes out to be, from here we have obtained our HP is equal to 1.42 meter. So this is location of center of pressure from your free surface, vertical distance here. Okay, okay, sorry, I made a mistake here. So like this distance here should be this one. Okay, so this is not HP, this is your F into, so distance will be your AC, that is L minus HP. Okay, this is your L minus HP. Okay, so this value which we have calculated here isn't correct. So from here we will obtain our HP. So this term come out to be 200 something. Okay, 200.28, and after it was multiplied by sine 60. Okay, so let's solve it again. So 5.7777 into 2 divided by 5 into 3 to the power 2.5 minus 2 divided by 7 into 3 to the power 3.5. Okay, this value into root 2 into 850 into 9.81 into sine 60. Okay, now divide it by 140,450. So we have obtained is 1.64. Okay, so this L minus HP by sine 60 value is equal to 1.64 meter, and this this value is from your base. Okay, so let's say that if I say this value is YCP, so this is your YCP. Okay, but if I talk about from the free surface, that is a value of HP, so this becomes minus L is your 5.77 into sine 60. So from here we have calculated our HP is equal to 3.57 meter. Okay, I hope you get this point now. So with this, we are done with our this session. Thank you.